Hi, ladies and gentlemen. I am Canbolat and senior year student in our department. And today I'm going to talk about my EEE STAR project. First of all, I would like to thank our esteemed assistant professor, Emine Bostancı, for her efforts and for giving us the opportunity to work on this project. In this project, which is called Effects of Electric Machine Characteristics on Electric Vehicle Performance, I studied with my friend Zeynep Çöplü. I also want to thank her for the perfect teamwork. All right, let me start with the overview of this video presentation. After a brief introduction, I'm going to talk about the important points of modeling of an electric vehicle on MATLAB. Then I will try to explain our methodology to model BMW i3, which is the observed vehicle by us. And finally, I'm going to express our simulation results for this vehicle. Most people think that the electric vehicle technology is a new trend. However, I can say that it's definitely not a new technology. You can see on the screen one of the first electric vehicles. This photograph was taken maybe 200 years ago, and historical travel of the electric vehicles has been started at those years. As I said, first electric car was manufactured in the early 19th century. In those years, although the range of electric vehicles was low, they were preferred against the IC engine vehicles because electric machines have self-start property and IC engines did not. At the beginning of the 20th century, this important property was gained to the IC engine cars. After that point, electric vehicles demand fell dramatically. In other words, this crucial technology was almost left to die. The sad point is the inventor of the self-start IC engines was an electric engineer. In 1973, you all know that the oil crisis broke out in the world and the price of oil had been doubled in one night. This price change pushed people not to use their cars. At these times, the value of electric vehicles, which were thrown aside years ago, was understood since there are no electric vehicles in the market and people restart to use cars. You know that it's a horse car actually. Nowadays, we live in times when electric vehicle technology is on the rise again. But what are the advantages of electric vehicles? Let me start with their efficiency. The efficiency performance of electric vehicles is better than the IC engine cars since they can regenerate energy. Moreover, they have fewer mechanical parts and more technological parts. Actually, this is a second advantage of them because they are adaptable to the new technologies. On the other hand, electric vehicles do not emit exhaust fumes. In other words, they are nature friendly. And as I mentioned before, this technology is independent of the oil price, since the price of electricity is more stable than the oil price. Let me continue with the electric vehicle types. As can be seen on the screen, there is no one type electric vehicle. Hybrid electric vehicles and battery electric vehicles are the most popular ones. In the scope of the project, we focused on the battery electric vehicles. We can divide the components of standard battery electric vehicles into three subgroups. The first one is the electric machine part. It's not a motor since, as I said before, regenerating energy is the most important property of an electric vehicle. Therefore, this machine can operate both in motor and generator mode. As you already know, the battery is the energy storage component of the battery electric vehicles. Controlling and protecting the battery is made by the battery management systems, in other words, BMS. And obviously, the machine operates with AC, and the output of the battery is DC. Therefore, there should be some power electronic components in these battery electric vehicles. Now we can move on to the second part of this presentation, the modeling of an electric vehicle. First of all, to make simulations on software, the longitudinal dynamic analysis should be done. In other words, forces that are applied to the vehicle should be estimated. In the end, these parameters of the equation, which can be seen on the left side of the screen, should be integrated into our analysis. Battery modeling should also be considered, since as can be seen on the right side of the screen, the output voltage of the battery is not constant. It depends on the battery material, operating temperature, and state of charge value. Therefore, the output voltage should be updated considering the energy level during the simulations. The components in an electric vehicle have variable efficiency. On the left side of the screen, the efficiency curve of the BMW electric machine and the inverter is shown. In other words, the combined efficiency curve. Clearly, it depends on the torque and the speed values of the operating points. Finally, to observe and make reasonable comparison, electric vehicle performances should be observed on a test cycle. In the literature, there are some common driving cycles that manufacturers use these cycles, such as VLTP, NADC, etc. After understanding the milestones of modeling an electric vehicle on the software, we start to research the parameters of BMW i3. The datasheet presents lots of information about the car, such as the battery, motor, and physical parameters, etc. On the other hand, they give some information about the performance of the BMW i3, such as acceleration and range performance. During this project, we studied lots of MATLAB codes, and you can see the most important three of them. These codes help us to integrate the real efficiency of the vehicle and to observe the performance of the vehicle, actually. Let me start with the combined efficiency map code. As you remember from the 3 pages before, I shared the combined efficiency of BMW i3. And by using the curve fitting method on MATLAB, we get an equation depending on torque and speed values at the operating points. This equation is used to analyze one cycle performance on the vehicle. As I showed before, manufacturers of the BMW i3 states that the range of the vehicle is around 285 to 315 kilometers in VLTP test cycle. So our range calculation also starts with defining the VLTP test cycle. Then, given physical parameters were integrated into the system, to observe the range performance of the BMW i3, the vehicle needs to be performed on one cycle of the VLTP again and again. Therefore, this range calculation code jumps to the one cycle code, which I'm going to talk about in the next slide. At the end of each loop, this code updates some of the parameters, such as depth of discharge, which is the consumed energy in this battery. And if this energy exceeds 90%, the system stops due to some safety issues. In other words, the range calculation is over. In the one cycle code, all the parameters should be updated for each time step. As mentioned before, the efficiency depends on the operating point, and the electric machine can operate even in a generating mode. Therefore, all the parameters should be calculated and updated to make this analysis more clear. All right, let me continue with the last part of the presentation, which is analysis results. I'm going to talk about 4 different analyses. The first one is the VOT analysis. I mean the wide open throttle test. In this test, full power is given and acceleration performance is observed. The time from stationary to 100 km per hour is one of the outputs of this test. Torque speed analysis shows the operating conditions and gives a chance to observe the limits of the vehicle. By using the equation getting from the curve fitting method, as you remember that, the average efficiency of the whole operation in one cycle can also be calculated. Finally, until the battery discharges almost fully, the vehicle run in VLTP cycle again and again to observe the range performance of the vehicle. Let's start with the VOT analysis results. As you know that electric machines have 2 operating conditions. One of them is base speed and the other one is the field weakening regions. The speed that the operation mode of the machine changes is called critical speed value. At that point, the torque of the machine is maximum. For BMW i3, this speed is around 73 km per hour. And the vehicle reached this critical velocity in 4.7 seconds in our simulation. Also, the vehicle reached from stationary position to 100 km per hour velocity in 7.3 seconds, which is exactly the same as the datasheet value. This shows that our MATLAB modeling of BMW i3 is very realistic actually. Also, we can reach the time to reach maximum velocity both from the critical velocity and the stationary position. The results of them can also be seen on the screen. As the datasheet of the BMW i3 states, the maximum torque of the machine is 250 Newton meter. However, as you can also realize that the simulations shows that the machine did not reach those limits. This is caused by the structure of the VLTP actually. It's not the best way to observe the performance of an electric vehicle since we cannot observe the limits of the machine. Now let me show the VLTP structure. As you can see that there are limited sudden acceleration and deceleration in this test cycle. Therefore, the regeneration rate is around 10%, which is low for an electric vehicle actually. The total length of this cycle is around 23 kilometers. And it can be seen that this cycle includes two different driving conditions actually. The first one includes first 1000 time steps, which represents the still driving. And there are some stopping times, and generally speed is very low in that region. The last 800 time steps represents the urban driving. This part includes sudden acceleration and decelerations, and comparing to the still driving, the vehicle can reach higher speeds. By using the equation getting from the curve fitting method, we calculated the average efficiencies of the BMW i3. In general, total efficiency is calculated at 87.24%. And this rate decreases to 83.67% for the city driving. For highway driving, this rate increases up to 93.21%, which is expected actually. And this rate also shows that the electric vehicles are very efficient, especially in highway drivings. As mentioned before, to observe the range performance of the BMW i3, the vehicle was run on the VLTP over and over. After the 12 cycles, the depth of discharge value exceeds the specified level, and this 12 cycles corresponds to 276 kilometers. As you remember that the datasheet states the range around 285 kilometers, which is also very close to our simulation results again. And this brings us to the end of this project. Today, I tried to explain electric vehicle concepts and their advantages. Then I summarized the modeling method of a battery electric vehicle on the software. After that, I gave some important parameters to make realistic modeling of the BMW i3 as much as possible. In the end, I showed our analysis results by comparing the datasheet values. These analyses gave us lots of idea on the possible effects of the improving electric machine in electric vehicle. In the near future, we are going to investigate these possible effects by changing the electric machine parameters. Thank you for listening to me. If you have any questions about the project, please do not hesitate to contact me or Zeynep.